Hi, my name is Indrajit Dhawan, and today I will give a talk on high dimensional time series forecasting. So let me share my screen first and get to the slides. Okay, so I will talk about a particular method that we've developed for high dimensional time series forecasting, where the dimensionality is very high, could possibly be in the thousands and even the millions. And we use a deep neural network to do this high dimensional forecasting. And the essence of the method is that we use a global method, but then uh, use that global method to act locally within each dimension. And this is based on two papers that have appeared in Europe. So the last 3-4 years, the first one appeared in 2016 on temporal regularized matrix factorization. The main content of my talk is from a NeurIPS paper that appeared last year, 2019. Okay, so high dimensional time series forecasting might have a very large number of correlated time series, so up to tens of millions. It has many applications, for example, in predicting traffic, weather patterns, and also in demand forecasting. And the essence is that then the forecasted values can be used for critical downstream tasks such as planning and inventory stocking. And so what we desire is that the forecasting method should be scalable because we have so many different time series. And of course, we want the results to be, the predictions to be accurate. So as an example, you can think of demand forecasting for shopping, where we want to try and predict future demand for millions of products in the catalog, right? And this is especially useful for inventory planning and being able to make these products available for customers. And sometimes you can have correlations which might not be obvious. And that's what the really big advantage of trying to do high dimensional time series forecasting, right? So for example, we've seen in recent times that we have N95 face masks and toilet paper. And what's happened is that these have actually been somewhat correlated over the past few months. And beneath that, there is some reason, right, which is that when you have N95 masks, people are staying more at home. And as a result, there is increased demand for toilet paper. Discovering these causal relationships is very hard, but the data will show that if you look at these time series, that there is a correlation between them. So the question is, can we exploit these correlations so that we can actually do more accurate time series prediction and also develop methods that can be more scalable? So the setting is that we have these different dimensions. So each row here represents a dimension, and each column, which we haven't explicitly marked out, is a time point. So for example, that might be a demand for a particular day, right? And so what we will do is we will and the job is to forecast into the future. And so we kind of simulate it by looking at it, there being a training window or a history of knowing the time series before a time t, and then we have a forecasting window after time t. So we'll use this notation. N will denote the number of dimensions or the rows, right? Or the number of items for which we are doing the forecasting, number of time series. And then we will assume that little t is the training window and history, and then tau is the forecasting window. And the time series will be represented by this matrix Y. So the dimension of this matrix Y is n rows and t plus tau columns, and it is divided into Y TR, which refers to the training window, and YTE, which represents the forecasting or the test window. And just to remind yourself, the setting that we have is very, very high dimensions. And so N can be in the order of tens of millions. We'll also assume that we have covariates that either are known in advance, usually known in advance, but also we might actually be able to derive covariates looking at the different time series. And one of our methods will do that. So we denote the covariates by Z, and we assume that the covariates are actually present for every combination of dimension and time point. So as a result, this is a three-dimensional tensor with dimension n t plus tau times r. So there would be covariates that could depend only on the dimension. For example, if you are trying to do demand forecasting, these could be text features of the products. We could have covariates that depend on the time index only. For example, day of the week or days from the nearest holiday, which might be useful in being able to predict the demand at a future or at that particular time. And then, like I said, we assume that we also could have covariates that depend on both time and dimension. So, of course, time series prediction is a very, very well-studied problem. And classical time series forecasting has research has spanned several decades, autoregressive models, linear state space models. But usually when you look at the literature, usually it's that you have one model per dimension. There are vector ARIMA methods or state space models that can scale to, I just want to say, modest number of dimensions, because here we are in our setting, we are talking where n could be tens of millions, right? So these vector ARIMA methods scale to thousands, and it's just hard to scale them to very large number of dimensions. So recently, there has been a substantial amount of work on using or adapting deep learning solutions for time series forecasting. So there are these LSTM methods, deep AR and deep space, state space methods. Then there are these temporal convolution based methods. The methods usually are trained, these methods are trained on the whole data set, but usually most of them at prediction time do not take all the items or all the dimensions into consideration, but only generally look on local paths per dimension. And if you try to scale them to look at all the dimensions, they just don't scale. And the scalability is limited by the number of parameters in the input and output layers. So there have been methods that try and capture global information during prediction. So the first method that I mentioned over here, TRMF, or temporally regularized matrix factorization. I'll talk about that a little bit later. That's basically work done by me and my research group and was published in NeurIPS in 2015. And then there are a couple of methods, and we will talk about them a little bit later. So one of the questions is, why think globally? And let's come back to the example that I had initially given, which is on demand forecasting. So most deep learning methods will train on the whole data set through mini batch stochastic gradient descent, SGD, and will basically go through the entire training data. But during prediction, the forecast is typically the model applied on only the local past per dimension. But what could happen is that there may be correlations, as I suggested before, there may be correlations across this different time series, which can actually help in making better predictions, right? So for example, this correlation, which is not obvious at first, looking at the descriptions of the items, for example, between masks and toilet paper. And what further can exacerbate the problem is, and this is where these methods that look at all the dimensions can be helpful, is that it could be that some of these that there could be many missing values. For example, in this data, for example, when products are no longer available, as we saw a few months ago. But it's also important to act locally, because if you the demand or sorry, the time series for a particular dimension is really determined by what happens locally. Maybe what is the product quality of that product. And so it's very important to think globally, but then act locally. So let's summarize the method that I'm going to talk about. So this is, so the remainder of my talk will be focused on this method called DeepGLO. So it corresponds GLO for global local model. And so this is the newest paper that was published last year. Think globally, act locally. It's a deep neural network approach to high dimensional time series forecasting. So let me first try and summarize the content, the big idea behind this research, and then I will dive into details. So what we do is, in this method, we develop a global temporal convolutional network, which is based on matrix factorization techniques. So it is matrix factorization regularized by the temporal convolution network. And this is inspired by our previous work on temporal regularized matrix factorization. And I'll come more to that. So this method can actually capture global information during prediction, but we want to try and adapt it locally, because that is very important. Because many times when we have these very, very high dimensional time series, there's a lot of variation in scale among the different between the different dimensions. So for example, there might be certain time series which are kind of hover around 0, and there are other time series which could actually have much higher or much larger scale. So what the final DeepGLO method will be a combination network, which is a temporal convolution network that combines the predictions of the global model with the local past. Okay, so now let's get into details. And this is based upon the work that we published in 2015, this is the temporal regularized matrix factorization work. So we put it in the similar setting where you have the training data, YTR, the test data, YTE. And so when we were looking at this problem, one of the things that we were trying to do is handle missing values, right? And so the idea was to use the matrix completion or low rank matrix factorization techniques on this training data, the time series training data, to express the time series as a linear combination of k basis time series, right? So we have these k basis time series being x over here. X, the matrix X represents the k basis time series, and then F represents a particular linear combination that we get to try and reconstruct the original time series. But this method is, you cannot just in a very naive way try and incorporate matrix factorization techniques. The critical aspect of this work is to how do we actually preserve temporal patterns in XTR, and how do we respect the fact that it is a time series predictive model. So usually matrix factorization techniques have something like this as the objective, and there is a separate regularization on X, which is similar to the one on F. So here, the factorization is f times x, and we are looking at the square loss. And so the important aspect about it being a time series is that in this TRMF work or paper, we did a regularization on the basis time series using an autoregressive regularizer. So if you look closely over here, what we are saying is that in this XTR, we preserve this order. It actually has this autoregressive structure, and we are trying to regularize it using that. So that XS, the time series, is actually a linear combination of the time series at previous time steps, right? And we can actually, in this method, the script L refers to the previous time steps. So you can, for example, have, if these are time series represent daily measurements, then in this set of lags, L stands for lags, then we can either have, short, immediate past. So L could be 1, 2, 3. And if there is some weekly or seasonal pattern in the data, for example, weekly, then L could have, 7, 14, and so on in the indices. And if there is monthly pattern, then 30. And if there is a yearly pattern, then 365. So all these were um, um, in this method, WL are not fixed, but they are actually also figured out during the computation. So this was the objective of the temporal regularized matrix factorization, right? So given Y, we want to try and find out F, X, as well as these parameters of this autoregressive model, W, that explain the factor X that represents the basis of the time series. So that was previous work. And in practice, TRMF actually worked quite well. So here are results that I presented that were in the TRMF paper. And the global model does better than the simple local AR1 models on average. And these are 3 different data sets that we tried our method on. And we used somewhat standard metrics, normalized deviation, that's actually also called WAPE, and this normalized root mean square, right? And in comparison, we compared it to methods like where we do SVD followed by a simple AR1 process where we don't learn any weights. And we see that the normalized deviation and the normalized root mean square error are much better. But there is a drawback to this method because it focused too much on the global aspect, right? So, but I'll come to that a little bit later. So one of the things that with this method was that, it is a linear combination of, so if I go back to this slide, so we are expressing each of the original time series as a linear combination of these basis time series in X, and we're just using a linear combination. So one of the things, when you look at deep learning is, well, can we actually get nonlinear, can we incorporate nonlinearities in a better way? So that is one of the, so let me explain that. So if I look back at the, if I look back at the global model, this is what we do in temporal regularized matrix factorization, right? Where we have these autoregressive model to explain the factor X. Well, we can replace that by a temporal convolutional network TX that can explain the factor. So instead of having, like if I go back to the previous slide, instead of having this particular regularizer, right, which is an autoregressive regularizer, we now have a temporal convolutional network regularizer. Okay, so and this can potentially capture nonlinear temporal patterns. So what is this regularizer? So let me step back a little bit and talk a little bit about temporal convolution. So temporal convolution is like a variation of a one-dimensional convolution where we can have exponentially increasing dilation or split connections. For example, in this figure, the dilation is 2 at hidden layer 1, and it's exponentially increasing with the layers. So, sorry, it was 1 at hidden layer 1, 2 at hidden layer 2, and it is 2 to the power k minus 1 at hidden layer k. And that way you can actually pretty quickly support large dynamic range or look back with few parameters, right? It'll be exponential with the number of hidden layers. And so, here we are trying to predict yj hat, and the variation from a traditional convolution is that we don't want to look at the future or the present to predict yj hat, right? So we are only looking at things in the past, and this is the structure of the network. And then using deep learning, we can try and learn these weights that are part parameters of this convolution, or basically along these directional arrows. And so the output of this convolutional network will be, so we denote this convolutional network temporal convolution by T. It takes the input over the set of indices or dimensions in I, does it for the time points represented in script J, or that's the training data. And then similarly, we look at the coefficients, the covariates over here that are either given or could be derived. Theta is the parameters of the convolutional network. And then we are using this to predict at the future time points, right? So J and J plus 1 at the next time step. Okay, so one very important aspect when you have very, very high dimensional, a lot of time series, that means you have very high dimensional time series problems, is that the scale can actually be different, right? So in particular, we use this data set called electricity. And this is, I think, the electricity consumption in different households over, I forget what the time period we do it, but it's daily hourly electricity consumption over a long period of time. So, some places the consumption can be very high, and then in certain time series, the consumption is actually very low. So, and this is very typical, right? If you look at the demand forecasting problem, certain products or items are just not going to have that much demand, whereas some other products or items would have very, very large demands. So this is a very important issue, and that's one of the reasons why we want to try and combine global predictions with, think globally and act locally. So, but just before we get into the details of that, how do we deal with such very high variations in scale? So typically these data sets might need to be normalized. Otherwise, the training and the models diverge, and then the predictions need to be scaled back. But many times this correct normalization scheme is not evident and can actually lead to differences in performance. So what we will do is first, one of the first things that we do in our method is use a very simple initialization scheme for these temporal convolution networks that allows us to train on data sets with varying scales. And what is very important is we don't actually have to do any normalization. So the key intuition is to start with parameters such that the prediction is actually close to the average of the past values for a particular look back window. And then the variations then around this mean are relatively scale free, and then the network can learn as training progresses. So in particular, if you want, go into detail, the details are there in the paper. When there are D layers with only sort of one channel and the filter size is K, then we can actually set the filter weights to 1 divided by K, and then we can show that the look back window is, like I said, exponential in the layer. So 2 times K minus 1 times 2 to the power D minus 1. And then the prediction Yj hat is actually the empirical mean of the training data or that particular time series over the look back window. So once we initialize using this, we can let training proceed, and we found that actually works very well. So for just to repeat, for initialization, we set the filter weights to be 1 divided by K for a general filter size. And right now, we will just put the weights to the covariates to 0 during this initialization. And this leveled init method in practice itself actually does fairly well. And so here I've given these results of just leveled init. So if you look at the 2 rows, it is the temporal convolutional network with leveled init. And then the second row is temporal convolutional network with this leveled initialization, right? And what we find is that even on unnormalized data sets, leveled init actually performs much, much better than if we don't do this leveled initialization. And we are looking at the standard metrics that are used in time series forecasting, MAPE, WAPE, and symmetric MAPE. So, in particular, you can look at the electricity data set and the unnormalized one, and you can see that without leveled initialization, the temporal convolutional network does not perform very well, but with leveled init, it performs much better. And similarly, you can look at this data set, which is the wiki time series data set. Okay, so this is the global model, temporal convolutional network with matrix factorization. So we can get a temporal convolutional network TX that can explain the factor X and can actually capture nonlinear temporal patterns. And so this is the regularizer now that we have. In TRMF, we used an autoregressive regularizer, but now over here, we are using a temporal convolutional network as a regularizer. And training proceeds in alternate epochs, where in the first method, we train the factors, and in the second epoch, we train the temporal convolutional network. So just going into more detail here, we trained, for example, F, right? Given everything else, Y and X, we train F. Then we switch over to SGD on X. Training proceeds in mini batches with contiguous time slots. And then we get the parameters of the convolutional network, the temporal convolutional network. SGD training with teacher forcing. And the way to get global predictions using this global temporal convolutional network is we can actually predict X hat over the testing time window, which might not be just one step. So, we basically do a multi-step look ahead prediction from this T of X. And then to get the predictions for the original time series, right over here, we multiply the predictions by F to get the global predictions. Okay. So, but by itself, these are the global predictions. But like I told you that the local behavior of the time series is actually incredibly important. So here is now this is a pretty busy slide, which is, let me try and explain it. So this captures the final method that we have, which is DeepGLO, global local forecasting. So let's start with over here. So what we do is using the methods that I just talked about, over here, we get these global predictions. So once we have global predictions, so this represents the training data, this is the global predictions, and then we use another combiner temporal convolutional network, which we call TY. Remember the previous temporal convolution network was called TX, but the job of TY is to combine global predictions with local predictions, right? So, and the way we do it is that the global predictions are simply added as covariates over here. In addition to the covariates that we might have before, we add the global predictions as covariates, and then we use this temporal convolution network to get the final prediction and to get this multi-step look ahead. And then so the outcome of this is then that we get this, I've called it hybrid, but this is the final prediction for our method. So this y hat represents the final prediction. So right, so so in practice, we found that this method actually outperforms most other methods and is actually reasonably scalable. So these are the data sets that we've tested on: electricity data, traffic data, wiki data. These have also been mentioned. And I think in one of this is also a traffic data, I believe. So these are the characteristics of the data. So N is, in the hundreds, but in the wiki data set, we wanted to illustrate that it can be quite large. So it is 100,000. The number of time points varies. And then the way we evaluate the task is to perform rolling validation with window size tau W and the number of windows being NW, right? So like I think electricity data set and traffic data set are hourly data sets. So the window size is 24 hours. Okay? And these are just some characteristics about the standard deviation among the mean. So you can see that there is a fairly large variation in the electricity and the wiki data sets, which is the problem of scale that I mentioned before. So these are results. I know this is a pretty busy slide, but these results are also available in the paper. So DeepGLO is always among the top 2 models on all tasks without any a priori normalization, right? So if you look at these columns, this is the electricity data unnormalized, this is the traffic data unnormalized, and this is the wiki data that's unnormalized. And these are our proposed methods. So the local temporal convolutional method by itself, then the global temporal convolutional method with matrix factorization, and then finally, the DeepGLO method. And you can see that on the unnormalized data sets, it actually works quite well. On the wiki data set, you will see over here that the local method leveled in it itself performs quite well. These are the results that were reported in the paper. And we believe that what's happening over here is that the model ends up overfitting to the global predictions. We've been doing some follow-up work, and in more recent experiments, we've corrected this. We basically add some noise to the predictions, and that removes this overfitting issue. And then to compare the proposed local global our DeepGLO method or the global local method and its philosophy, we compare against methods which are just local only or global only. And then, this is the spatiotemporal graph network in a 2017 paper. And these are the comparisons of DeepGLO unnormalized and DeepGLO normalized with this particular deep learning method. We are unable to use it for the other methods, for the other data sets, because the graph structure is assumed to be known, and we don't have those values we don't have that known structure for the other data sets, but for this data set, this was available. But even on this data set, we can see that DeepGLO unnormalized actually does quite well. Okay, so this is kind of the conclusion of my presentation of the work that we've already done. And let me spend just a couple of minutes now on ongoing and future work. So what can happen in these global local methods is that, yes, I told you that how different dimensions can actually, because of correlations between them, can help in predictions. But many times what could happen is that not all global information is relevant and could actually hurt performance. So for example, demand forecasting for shoes might not have really any correlations with other items. And as a result, the performance can actually deteriorate if we try and take too much global predictions into account. And one of the other cases that it actually leads to scalability issues for very, very large data sets. Like I said, n in the tens of millions and so on. So to remove this problem, what we are working on right now is methods where we derive embeddings from local models and covariates to try and actually perform some sort of clustering for the time series. Then per cluster, within that cluster, we train a global model that's only for that particular cluster. And then we combine the cluster-wise global information with local model whose parameters are trained on the whole data set. So that's some work we've been doing. We've been seeing promising results, and hopefully we will report those in the near future. So that's it for my talk. I thank you for listening, and I'm going to stop recording here in a minute. But thank you so much for listening to my talk. Thank you. Bye.